Hello and welcome to my channel. In this video I will be talking about the software design principles I use to create the control software, and in this video we will also dive a little bit deeper how the control software is actually built up, which is a rather dry topic, so don't be surprised if the presentation is also a bit dry, but try to enjoy it anyway. So without further ado, let's start. Okay. So the main design paradigm I use to create the control software for the production plant you saw is object-oriented programming. While creating all the functions and function blocks, and especially the device control function blocks, I always imagined some sort of a class that you know from Java or C++. But since the Siemens implementation of the IEC programming languages for PLCs does not support object-oriented programming as Java or C++ does, I had to use some tricks in order to achieve something very similar. So let's examine this a bit closer. So basically, when I was creating the control blocks, I wanted to reuse as much code as possible. And in order to do that, I had to partition the code into several layers. And which layers are these? There are three main layers here. At the bottom we have the drivers layer, then the device layer, and the stations layer. Let's examine the first one. The drivers are basically the most basic form of control in the software, and these are directly responsible for switching on and off actuator signals. As you can see, there aren't that many of them. We have different types for different types of movement, basically. We have a driver for binary and bistable devices. We also have one for binary monostable devices. We have the same for with just one limit switch. We have one for analog devices, and then we have for movements which are happening stepwise. So let's move one layer up. Here we see the devices, and devices are basically wrappers around drivers, and their job is to add further functionalities to drivers like state machines, scripting capabilities, general control, and status information, which are common to all other devices. Of course, the devices can be composed of more than one drivers. For example, if we check out the palletizer, we see that it is composed of at least a binary monostable driver and a binary monostable one-limit driver, and it is also composed of a stepper driver. But if you check out the other blocks that it is composed of, we see that it is not only composed of drivers, but it can also be composed of other devices like the single item conveyor and a multi-item conveyor as well. As a matter of fact, the palletizer is one of the most complicated device drivers of them all. This is why it's composed of so many other blocks. And this follows actually a good design principle of object-oriented programming, which is composition. Okay, so let's move one layer up. We see that we have the stations here, and stations are basically composed of several other devices, and the only code they add to the program that exists already is a small amount of code that makes the devices work together through their standardized interfaces. Let's see how devices were defined and what interfaces they are providing. So basically, when I created these device function blocks, I imagined an abstract class behind them from which they can inherit. And this abstract class, the device class, a base class, would provide a common interface and internal structure to all of these devices. For example, each of these devices that you can see here have the exact same minimum interface, which consists of a control data, an IO data, a settings block, device communication with other devices, and a status data. Moreover, on the inside, they have common networks, which you will see shortly, which are shared between all of these devices. This way, it's really easy to not just find out how these work, but also fix something if something goes wrong, or create new devices based on this scheme. Of course, in a language supporting object-oriented programming, one wouldn't need to do this manually, but since, as I have said, the Siemens implementation does not support inheritance in any way, I had to basically emulate inheritance. So let's check it out how this looks like in real code. Let's open up TIA Portal. And let's open up a couple of these device function blocks, for example, the multi-item conveyor and, for example, a pick place device. Okay, so if we check out the interfaces of both of these devices, we will see that each of them, actually let's divide this up into then we will see that each of them share a common interface. For example, both of them have a control data, an IO data, settings, a conveyor in and out, connection UDTs, and a status. So it's all the same. The commonalities don't end here. So if we unsplit the editor and close this up, we will also see that some of the networks are also shared between these blocks which control very different devices. So we have the trigger logic, reset logic, and so on, output, signal control, and so on and so forth, which we will also find in this block: trigger logic, reset logic, output, signal control, stage control, and so on and so forth. So this somehow resembles virtual functions which would have been defined in a base class, but since we do not have base classes here, I basically needed to do this manually. Moreover, I also try to use the design principle of encapsulation, meaning that only data that should be accessed from the outside can be accessed from the outside. Of course, this is not totally achievable in this implementation of the programming languages, since one can always access the internals of the data block belonging to the function block. But to encourage using a proper way of accessing data, I define the settings and status UDTs, where the settings are basically the setters. So one can think of these as setters, and the status UDT, we can think of it as a getter, and these are responsible for providing data that we should be able to access from the outside. Okay, let's close this all up too. Of course, these device blocks don't only contain the blocks that we saw here, but they also are made up of several other common blocks which are responsible, for example, for the scripting support, or the state machine handling, or the inter-device communication. But I did not list them here because it would make this diagram really hard to understand. Thanks for watching. Bye.